NASA has recently unveiled a series of groundbreaking findings that have upended long-standing scientific beliefs about Neptune. Traditionally considered a distant, cold, and relatively stable ice giant, Neptune has long been overshadowed by the dramatic rings of Saturn and the immense size of Jupiter. Positioned nearly 3 billion miles from the Sun, Neptune was thought to be well understood, defined by its high-pressure ices, dense hydrogen-helium atmosphere, and powerful but predictable weather systems. However, this perception has been radically altered by new data gathered from both Earth-based telescopes and spaceborne observational instruments. What researchers have discovered is not merely a refinement of existing models, but a fundamental challenge to our understanding of Neptune's interior dynamics, magnetic characteristics, and its broader role in planetary evolution. One of the earliest and most significant revelations came from unusual readings of the planet's magnetic field, data collected through a combination of the Hubble Space Telescope, the Chandra X-ray Observatory, and radio spectrometry equipment aboard various probes and orbital platforms, revealed startling inconsistencies in Neptune's magnetic topology. Unlike Earth, whose magnetic field is roughly aligned with its rotational axis, Neptune's magnetic field is tilted by about 47 degrees. While the tilt itself was previously known, the surprise came when scientists observed that the degree of this tilt was changing in real time. Within just a few years, a blink in cosmic timescales, parts of the magnetic field had shifted unpredictably, suggesting a dynamic and possibly unstable planetary interior. Adding to the intrigue, Neptune's atmosphere began exhibiting unusual behaviors never before observed. The planet, which has historically been home to colossal storms, such as the Great Dark Spot, is now revealing new atmospheric phenomena through infrared and ultraviolet imaging. Sudden bursts of emissions in these wavelengths suggest rapid and potentially explosive chemical or thermal reactions deep within the planet's clouds. Rather than a quiet, frozen world, Neptune is now seen as a planet full of chaotic, high-energy processes. Researchers found a direct correlation between these atmospheric outbursts and fluctuations in Neptune's magnetic field. One particular sequence of pulses recorded over a 16-hour period aligned almost perfectly with magnetic field oscillations, leading scientists to theorize that Neptune's internal dynamics might resemble those found in active rocky planet Solar. Even stars. This possibility implies that Neptune's core may not be a static frozen mass, as once believed, but rather a fluid and energetic mixture of superionic water, exotic ice phases, and metallic hydrogen. These materials could interact in complex ways, affecting both the planet's internal structure and external atmosphere. Further complicating the picture, researchers documented a dramatic temperature drop in Neptune's stratosphere, nearly 10 degrees Celsius over just 2 Earth years. This cooling trend directly contradicted earlier climate models, which had predicted a slow warming cycle. The abrupt nature of this change could not be accounted for by known seasonal variations or solar activity, hinting instead at a deep planetary transformation. Theories began to emerge, ranging from magnetic pole reversals to internal convection shifts, but none have yet provided a comprehensive explanation for all the observed phenomena. Another particularly striking finding came from gravitational field measurements, which indicated an unexpected drop in density within certain regions of Neptune's interior. This anomaly suggested the possibility of a large internal void or cavernous zone, appending traditional models that assumed a uniformly compact structure beneath the planet's outer layers. If confirmed, this would not only rewrite our understanding of Neptune's geological profile, but could also force scientists to revisit theories about how ice giants form. Rather than a slow, steady accumulation of gas and ice, Neptune may have experienced a violent origin, potentially involving a massive collision that left a structural scar within its core. Such a history would set it apart from its planetary cousin Uranus and even more so from the gas giants Jupiter and Saturn. At the same time, Neptune's faint ring system began to show unexpected activity. Once considered a static collection of dusty debris, likely remnants of shattered moons or comets. The rings are now displaying clumping and shifting behaviors in high-resolution images. These movements suggest the influence of unseen forces such as shepherd moons, gravitational resonances, or dynamic internal ring processes. The changes occurred too quickly to be explained solely by classical physics, leading some to speculate that Neptune's gravitational field might itself be fluctuating, possibly as a result of the same internal or magnetic disturbances seen elsewhere. If a planet's gravity can vary, even subtly, this would have profound implications for our understanding of mass behavior in celestial bodies. Perhaps the most puzzling of all the recent discoveries are the bursts of radio emissions that appear to be unlike any previously detected in the solar system. These emissions, lasting just milliseconds and repeating at irregular intervals, don't match the known patterns of auroral radiation typically caused by solar-wind interactions. Instead, they seem to originate from within the planet, almost like rhythmic planetary pulses. Their irregular nature and origin make classification difficult, and ongoing research has proposed a wide range of potential explanations, from resonant waves in superionic ice to transient plasma loops within the atmosphere. Each new data point further complicates the image of Neptune. Far from a static, frozen outpost, the planet now appears as a highly active, mysterious world with properties that challenge long-held astrophysical models. Some researchers are beginning to draw comparisons between Neptune and distant exoplanets, especially hot Neptunes that orbit close to their stars and exhibit intense magnetic activity, atmospheric escape. If Neptune shares physical processes with such worlds, it may serve as a valuable analog for understanding planets beyond our solar system. There is also growing interest in Neptune's influence on its surroundings. Situated at the edge of the solar system, Neptune is in close proximity to the Kuiper Belt, a region filled with icy bodies, dwarf planets, and possibly undiscovered celestial objects. Shifts in Neptune's magnetic field or gravitational pull could subtly alter the orbits of these Kuiper Belt objects, KBOs. Indeed, some astronomers have already noticed small but measurable orbital changes in several larger KBOs, raising questions about Neptune's possible role in shaping the structure of the outer solar system. Even Neptune's moons are drawing renewed attention. Triton, the largest of Neptune's satellites, is especially fascinating due to its retrograde orbit and nitrogen geysers. Recent scans of Triton's surface have revealed irregularities in its crust that may be linked to Neptune's changing magnetic environment. There's speculation that tidal or magnetic forces could be causing internal heating on Triton, suggesting real-time interactions between the moon and its host planet. These findings raise broader questions about how planetary systems behave as interconnected networks, especially in cold and distant regions of space. All these discoveries have enormous implications for theories of planetary formation. The dominant model has long suggested that the solar system formed gradually, with outer planets like Neptune forming from ices and light materials far from the sun's heat and pressure. But signs of violent collisions, structural anomalies, and dynamic internal processes suggest a far more turbulent origin. It's possible that Neptune underwent early migrations, collisions, or gravitational interactions with yet unseen massive bodies. This turbulent past challenges the assumption that the outer solar system evolved slowly and quietly. Ultimately, these revelations reinforce a critical insight. The outer planets are not the quiet, frozen relics once imagined. Just as explorations of Jupiter and Saturn have revealed complex atmospheres, layered interiors, and potentially habitable moons, Neptune is emerging as a frontier of mystery and discovery. What makes Neptune's case especially compelling is how little direct exploration has been done. The only spacecraft to have visited it was Voyager 2, which flew by in 1989 and provided only a fleeting look. Since then, all insights have come from remote sensing and advanced modeling. Yet despite these limitations, the planet has begun to reveal secrets that challenge fundamental assumptions in planetary science. As interest in Neptune intensifies, Space agencies are actively considering future missions to study the planet. More closely, proposals for orbiters or atmospheric probes are being discussed, with the goal of confirming or refuting the many new theories about its magnetic field, core structure, and atmospheric phenomena. Though such missions are still in the conceptual stages, the urgency to investigate Neptune further is growing. Each new finding hints that this distant world may hold key answers to universal questions about how planets form, evolve, and function. Under extreme conditions, for now, Neptune remains a vibrant enigma at the edge of the solar system, constantly challenging our scientific understanding. Its evolving portrait is a powerful reminder that the cosmos is full of surprises, and even the most distant, seemingly stable planets may harbor astonishing secrets waiting to be uncovered.